So again, we'll be discussing on statistical data analysis techniques in today's class. And at the end of today's section, you should be able to describe statistical analysis techniques. You should be able to describe primary measurement skills with appropriate examples. You should be able to define normal distribution and its characteristics. You should be able to highlight appropriate tests under parametric and non-parametric statistical analysis. You should be able to compute t-test, f-test, chi-square test, and ANOVA analysis of variance using MS Excel. You should be able to describe non-parametric statistical tests and the associated tests. You should be able to describe univariate, bivariate, and multivariate analysis. And finally, you should be able to highlight methods of data presentation with suitable examples. So these, among others, are what you should be able to do at the end of today's section. Without any further delay, let's get started. Now, let me make something clear before we proceed. Analysis will come after you have done your data collection. And some of us may not do our data collection until after our proposal defense. So meaning that whatever you will be doing from today onward until the last class will be something that you will be needing after your data collection, because all we'll be discussing now is all about analysis. So meaning that you have enough time to practice on how to carry out a particular analysis on certain data or on the data you have collected. You must know the kind of research you're doing. You must be able to identify the kind of data you'll be collecting. You must know the kind of results you are expecting. So with that, you'll be able to determine the kind of analysis tests you will be carrying out. So once you know that, all you need to do is to learn how to perform those tests. If it's easier for you to perform on Excel, you can use Excel. If SPSS is a data tool, in your own case, you can also use SPSS. All that matters now is for you to be able to identify which tests will give you the kind of results you want according to your research needs. Okay? So, statistical analysis techniques allow researchers, businesses, and organizations to make sense of data and guide their decision making. Because you have collected some data, basically raw data. You need to analyze them. You need to put them together and get some views in order for you to be able to ascertain a particular fact. Last time, we were talking about problems, research problems, or research challenges. And we mentioned, if you remember, that the fact that something occurs as a problem to you doesn't mean that it's a problem to the society. You need public views, public opinion to be able to determine whether that particular problem is indeed a problem before you can carry out a research on how to mitigate or how to reduce or how to find a solution to that particular challenges or that particular challenge. So after you have gotten people's view, you analyze their view, only then, based on the result of the analysis, we'll be able to guide you to determine whether it is actually a problem or not. And that is the decision you are making. So statistical analysis techniques allows researchers, businesses, and organizations to make sense of data and guide their decision making. Another example, whether you have ever wondered why Samsung, Apple, whenever they release a new product, people always buy. People always queue to buy, even before they release them. Why? Because they produce those, they created or they developed those products based on what people ask, based on people's specification. Now, how did they gather all the specification? They carried out the research, they collected sample, they collected data. They collected research data, they collect data from their target group, which are actually the customers. So it is from this survey that they were able to identify what feature the people really want in their smartphones. What kind of product the people really want? It's not that it's not the company that is kind of, thinking ahead of the masses. No, it is real masses that do their own and they produce accordingly. That is the purpose of research. So with the help of statistical analysis, it guides them to produce the correct products that people will be eager to purchase once they release it into market. There are different types of statistical analysis techniques that can be applied to a wide range of data, also industry as well as applications. We have different types of statistical analysis techniques. So knowing the different statistical analysis methods and how to use them can help you to explain data, find patterns, and discover trends in your research. So choosing the appropriate statistical tests for each research question is the most challenging feature in statistics, but also the most necessary in order to eliminate measurement errors. If you could remember last week, I was telling you that you should know the correct graph to choose when you are trying to do some kind of graphical presentation of certain variables. I remember I mentioned this when I was discussing about continuous and discrete variable. So same thing happens here. You must be able to choose appropriate statistical text in your work. If you choose the wrong one, you may actually result to some form of some sort of measurement errors. So that is why you need to understand your research needs. That's the first step. Then identify the kind of data you will be needing for your research. You also need to identify the source of data, your data collection method and instruments. Where do you want to get it from? Your target group also plays a role. You don't just start collecting data from random people. No. You need to know who are the people that will actually give you what you want. And those are your target group. Take, for example, you are doing a research that is applicable to the health sector. Let's say hospital, for example. And suddenly you came to the university, you went to faculty of education or faculty of business, and started collecting data from there. Definitely you'll be collecting you are collecting data from the wrong people, from the wrong target group. Instead of you to go to the hospital and meet all the medical practitioners and collect your data there, you went to the wrong target group and you're collecting your data from them. Eventually, such will lead to measurement errors. So you must be able to select your target group correctly. Then the kind of data you are trying to collect, the kind of measurements and the kind of measurement tools or collection tools you'll be using. Then after that, that will also determine the kind of statistical analysis method that will be applied on such data set. All of this is to prevent measurement errors. Once you get this correctly, then you are good to go. Now, before we proceed, let's quickly look at there are some primary measurement skills, which are we have nominal scale, We have ordinal scale, we have interval scale, and we have ratio scale. We have mentioned this in the last class. But again, just a brief recall. Now, for nominal scale, what are the basic characteristics of a nominal scale? Numbers identify and classify objects as yes or no. Common example could be student registration numbers, country of origin, and for marketing example in this regard, you can have classification, bank types, gender, something like that. And what are the kind of statistical analysis that can be carried out on a nominal variable? For descriptives, you can compute percentages and nodes. For inferential, you can perform chi-square or binomial testing, depending on what you are trying to investigate. For ordinal scale, the basic characteristics include numbers indicate the relative position of objects, but not the magnitude of difference between them. Common example could be ranks of the top 4 teams in the football or World Cup. The marketing example for this kind of scale includes a ranking of service quality delivered by a number of hotels. When we have satisfied, strongly satisfied, not satisfied, all those kind of things, agreed, strongly agreed, all those kind of things. Then rank order or report based on the universities. And what are the permissible statistics on an ordinal variable? We have for descriptive, we can compute percentile or median. For inferential, you can perform rank order correlation, Friedman, and ANOVA. For interval scale, the basic characteristic is the difference between objects can be compared. 0 points is arbitrary. Common examples could be like a temperature. And marketing example could be attitudes, opinions, index numbers, consumer behavior. And what are the permissible statistics for an interval scale? We have range, under descriptive, we have mean, under descriptive as well, we have standard deviation. And under inferential, we have product limit correlations, we have t-test, we have ANOVA, we have regression, and we have factor analysis. For ratio, that's a 0 on a ratio scale means there is a total absence of the variable you are measuring. And good example, a common example of a ratio scale is length and width. Age, income cost, sales, market share are all examples of marketing. For permissible statistics under ratio scale, for descriptive, we have geometric mean, which is center of number, and we have harmonic mean. For inferential, we have coefficient of variations. So these are some of the statistical analysis that can be performed on any of these scales. If you're going to understand this more, let's move further. Now, another very important area that you also need to take seriously is normal distribution. We're just going to mention this briefly now. We're going to discuss about this later, maybe next week. This is because whatever data you will be using and whatever kind of analysis you will be applying, majority of them is assumed to be normally distributed. That is why we have to know what normal distribution really is, especially when we're dealing with parametric statistical tests. Now, an important aspect of the description of a variable is a normal distribution. So it is a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. Now, why the normal distribution is so important? Because in most cases, the distribution of many statistical tests is normal, or following some form that can be derived from the normal distribution. So it also indicates the types of analysis that can be performed on the data. So if your data set you have collected fails the test of normality, then you use a test. There are different things that can be used on such data set. And how do we perform normality tests? We're going to look at that data. Then normal distribution is represented by a group of curves, means and standard deviation. The curves are symmetrical, which means that the mean, median, and mode are all equal, and it is always a bell shape. So if you look at the guy towards the right of the screen, this is an example of a normal distribution. While this is the mean, this is the mean, and the distance between the mean and the first point here is actually the standard deviation. Okay? So we are going to discuss more about this, but just to introduce you to what normal distribution is. Now, we have two categories of statistical tests. We have parametric statistical tests and non-parametric statistical tests. So parametric tests are hypothesis testing procedures which assume that the variables of interest are measured on an interval or ratio scale, and observations must be drawn from the normally distributed population. So, meaning that whatever test you have chosen under parametric statistical test, or your data sets must not fail the test for normality. Meaning that your normality test must not be violated. For whatever test you want to use under parametric test. So when the dependent variable is measured on a continuous scale, then a parametric test should typically be selected. I will take that again. When the dependent variable is measured on a continuous scale, then a parametric test should be selected. We have few types of parametric tests. One of them is t-test, we have f-test, another one is z-test, and we also have ANOVA test. The appropriate use of such tests require one to check whether the data fulfills certain assumptions or conditions. Now, what are these assumptions? The first assumption is that observation should be independent. Observation should be independent. That is, the occurrence of A should not affect the probability of B. Now, a second assumption is that data should follow a normal distribution with mean equals to 0 at the given variance. So meaning that it has to, test of normality must not be violated. So once your data sets fulfill these two assumptions, then you are good to go. Statistical tests such as Kolmogorov, Smirnov, and Shapiro-Wilk, and Agostino testing are used under the null hypothesis to test that the sample data fits a standard normal distribution. Meaning that to test for normality, these are the tests that we use. You can use Kolmogorov, Smirnov, popularly known as KS test, or you can use Shapiro-Wilk, or you can use the Agostino passing. So these three tests can be used to test for normality. We are going to use them, but we are going to use them on SPSS because it is easier on SPSS. Okay, so now, again, under parametric tests, one of the tests that can be carried out is t-test. T-test, we have a few types of t-tests. We have independent t-tests, which is otherwise known as student t, which can be used for one sampled or two sample t-tests. You can also have independent variables, males or females, Malay, Chinese, case control, depending on how your variable is. Then we also have peer t-test. When you have dependent variables such as before, after, two methods used on the same patients. Then another test under parametric statistical test could be ANOVA, where you are trying to compare between more than two groups. In this case, you have Malay, Chinese, and India. You have countries such as you have Malaysia, Singapore, Indonesia, and so on. So whenever you have more than two groups, then that's when you use ANOVA. There are some other conditions, okay? But basically, when you have more than two groups, that's when you use ANOVA. Then you have Pearson correlation. Correlation between two quantitative variables, such as we have weight and height or weight and age. These are just some of the examples of parametric tests, parametric statistical tests. We have t-test, we have ANOVA, we have Pearson correlation. Now, let's look at t-test. T-test, we're going to discuss about t-test later in detail. We have three types of t-test. Okay, but later we're going to come to that. Now, t-test is used when you have two conditions, and you would like to compare the differences between them to see if it is significant. So basically, we use t-test to investigate differences. We use t-test to investigate differences between groups. You have two groups, can be conditions, we are calling two conditions. And you want to compare the differences between them and see if that difference is significant or is statistically significant or not. So let's look at this example. In this example, I want to see if there's a significant difference between my two groups or my two conditions. So my data came from the same people. So meaning that I'm measuring the same population. Condition A was recorded in the morning, while the condition B was taken in afternoon. The same people. I've measured them twice. So if you look at this place, I have my condition A and my condition B. So the person with ID 2 was, I got 935 from him in the morning. And the same person, I got 978 from him in the afternoon. So I've measured the same person twice. One in the morning, and the other measurement was taken in the afternoon. So these are my groups. These are my two conditions. It can be group in the case, it depends on what you are trying to investigate. It can be group. But in my own case, I decided to use condition. Now, to find out this test on Microsoft Excel, there are some built-in functions that allow us to perform this kind of test. So these two functions they take certain parameters. And how do we use them? All you need to do, you click on the cell where you want the value of your t-test to appear. So once you select the cell, you need to type in equality sign, this equality sign, equal to. You need to type that sign. Then you type T. Whether you're writing in uppercase or lowercase, it doesn't matter. Just type T. Once you type T, there will be more functions that will be displayed. So, but we are interested in the t-test. So, because of that, you put dots and you type in tests. Whether you type it in uppercase or lowercase, it doesn't matter. Then once you type in test, you open your first, you type in open brackets, this open bracket. So once you type in this open bracket, now before I go there, now I don't want to go too technical, but again, I have to mention this to you. This T here is an object, okay, of the T class. So inside that object, we have few methods. So one of the methods is tests. So that test method is what we are trying to use. So that's why you're having this test here. Then this test has certain parameters. So those parameters need to be filled up before we can compute this t-test. So in order to fill up those parameters, you need to type in this open bracket. Then once you type in this open bracket, you will see it will be highlighted somewhere here. Now, it's asking for array 1, comma array 2, comma tails, and comma type. What does this actually mean? And another thing we notice is that this array 1 appears in bold. It appears in bold because this is the data that is that this particular function is expecting you to type in at this point. Once you type in the cell reference of the data set you want to use for array 1 and you type in comma, this will appear as a normal text, just like other text. And this array 2 will become bold, meaning that you need to enter the cell reference for the second array list. So once you do that, you put comma, this will also turn back to normal text and the tails will now be bold and so on. And once you are done, you need to type in this close brackets and type and hit your enter button. Only then you will get something like this, which is actually your p-value. Again, the array 1, in this example, the array 1 will be our condition A. While the array 2, this guy, will be our condition B, list of condition B. These values we have here. Now, under these tails, we have few options. We have just 2 options. One, if you have a direct hypothesis, that is, if you have a direct hypothesis that you know that something will happen. Let's say, for example, you say, okay, so event will occur. Okay, in this case, we are trying to investigate a difference, right? And we are saying that, okay, there's a difference between our null hypothesis, saying that there's a difference between the 2 conditions. That's our null hypothesis. Then, in that case, just choose 1. But if we don't know, we have no idea whether there will be a difference or not, or whether the difference will be significant or not, then just choose 2. I'll take that again. Array 1 is for the observation you have under your condition A, or it can be group A, it can be group, it can be female, it can be male. Okay? Then, for condition B, that is what you need to put for array 2. Therefore, tails, you have 2 options, 1 and 2. 1, you choose 1 if you feel like, if you have your null hypothesis that states that there is a difference between the 2 conditions. Then just choose 1. But if you don't have an idea, I don't know whether there's a difference or not. I'm not really sure. Then you choose 2. Then lastly, we have type. For this type, we have 3. That's why I said t-test has 3 types. You have 1, 2, 3. Okay? Now, you choose 1 if the data comes from the same participants. The data comes from the same participants. For instance, this guy here, these observations here, I said it earlier, I mentioned the same people, the same people. The same person with ID2 was mentioned in the morning for condition A, and the same person was mentioned in the afternoon, and the value that was recorded was written under condition B. So meaning that these values for condition A and condition B comes from the same person, and meaning that each of the participants of this research or this survey were measured twice. So in this case, my sample comes from the same participants. In another case, it may choose two if the data come from different groups. The data come from different groups, and the variance associated with each group are the same. Let's say this is a different group. This is another group. This one group is another group, separate groups. And you check their variances, and the variance of this is equal to the variance of this. Then you choose two. But if this is not the case, let's say you have two different groups, but the variance are not equal, then you choose 3 for type. Okay, I'll take that again very quickly. T.test, open brackets, R1 is for your first condition or group, comma, R2 is for your second condition or group, comma, tells you have two options here, 1 and 2. 1, if you have your null hypothesis that there is a difference between the two conditions, and you want to investigate, you want to check, you choose 1. But if you have no idea, you don't know whether there's a difference between the two conditions, then you choose 2. Comma, for type, we have 3 options here. You choose 1 if the data comes from the same set of people, from the same population, or from the same, you are from the same participants. Just like what I had here. Group A, condition A, condition B, the data recorded, the value recorded, observations were from the same people, the same person. For the participant with ID2 was measured twice. The participant with ID3 was also measured twice. The participant with ID4 was also measured twice, and so on. So meaning that the same person has been measured twice. So in that case, I chose type 1. But if that is not the case, let's say you measure different person for condition A, and you measure different person for condition B. These are two different groups. Let's say this is male. Let's say this, the whatever you got here, are for males. And whatever we have gotten here are for females. These are two different groups. Then, in that case, you check their variance. If they have equal variances, then you choose 2 for type. But if they don't have equal variances, then you choose 3 for type. Once that is done, you close this, type in the close bracket and press enter, and the value for your p value will appear wherever you have selected. Now, how do we now interpret this? What's the meaning of this figure? We check whether the value we have here is less than or equal to 0.05. 0.05 is the commonly used value for this kind of test. So we check whether it goes below, whether it's less than 0.05 or is higher than 0.05. And when you look at this, you see 0.02. If you round it up to 2 decimal places, which is 0.02 is less than 0.05, which shows that the difference between the two conditions is significant, statistically significant at 0.005, 0.05 level of significance. But if this value is higher than 0.05, then that means the difference between the two groups is not significant. That is the interpretation of this particular value you're seeing here. Okay. So how do we perform this? I've already shared the Excel sheet with you, so you can just follow as I'm. So now this is the same value I showed you just now on the slide, which you can always just put side by side so you can see clearly. Okay. Okay, you can see this is the same values that I'm having here. So what I'm trying to do is that I want to perform a t-test to check whether there's a difference between these two groups or not. I want my result to appear here in front of where I've entered. It's just a text. I just enter p-value. Okay. So I just select the text, the cell where I want the value to appear. So I selected this text. I'm in this cell and I press equal sign. You can see equal sign. Okay. And once that is done, I can type T. Now, after typing T, you can see we have T words here. But we are interested in this T test. So I can just say dot. Now, like I said earlier, this T is an object of the T class. So inside T class, we have other functions. Okay, we have T distribution, this word of T2, and so on. But we are interested in T test. So I type test. Okay, and I type in open brackets. So when I enter the open brackets, you can see I have all these parameters. And the array one is the array one appeared bold. Meaning that this is the data set this particular function is expecting me to enter at this moment. So I want to enter what I have in here into this place, the cell reference or what I have here. So what I need to do, I will click, hold, and drag. Click, hold, and drag, and release. You see, all the cell reference for these values has been automatically captured, and they are now here. The next cell reference is A2, this cell A, row 2. And the last one is A9. That's what we are seeing it here. Okay. Now, in order for me to move to the next array 2, I just need to put comma. And when I enter comma, you can see array 1 is no more, it doesn't appear bold anymore. So now array 2 is now selected. Okay, so I need to select, do the same thing I did for condition A for condition B. So I select again, drag down and release. Now you can see the cell references has also been captured. So I set comma. Now for the tails, I have 2, 1 or 2. So I have a feeling that there will be a difference between the two groups. So as a result of that, I go with 1. Okay, then I also put comma. Now type. We have 1, 2, 3. Paired if the observation comes from the same people. If sample equivalence, it comes from different group, but it has the same variance. But 3, it comes from different groups, but it doesn't have the same variance. Then I choose 3. But in this case, it comes from the same group, so I don't have to worry about 2 or 3. So I just choose 1. Then I type in the close brackets. Okay, I've supplied all the parameters. Whatever you have inside the open and close bracket are called parameters. So I've supplied all the parameters. All that needed to be done now is just to press enter. So once I press enter, the value will come up. Okay, now to make it easier for me, I'm already put 2 decimal places, so I can just do something like this. Okay, so I made it to 2 decimal places. So I have 0.02. So 0.02 is less than 0.05, which shows that there's a significant difference between these two conditions. So this is my t value. This is my value, this is my p-value, and this is my significant error. And this is what, based on this value, it shows that there's a significant value, there's a significant differences between these two conditions. Okay, so that is that on theta. We're still going to do more on this when we go to SPSS. Now, we also have F-tests. We use F-tests, or we can use F-tests to test whether the two variances of two populations are equal or not. So, going by the previous example, if your whatever comes from two different groups, and you want to test whether they have equal variances or not, then you can use F-test for this purpose. So the null hypothesis for F-test always states that the variances of both groups are equal, while the alternate hypothesis always states that both groups have different variances. Okay, so to do this, in this case, I've gotten another set of observations. In this, I have two different groups. These are female, these are male. So I want to check whether they have equal variance or not. So eventually, this is what I got. So you look at, when you get this result, you look at the F value and F critical one-tail value. So in this case, the F value is greater than the critical one-tail value. This is greater than this. So therefore, we reject the null hypothesis that states that variance of both groups are equal. And if you want to look at it, this is mean. This is the mean for female. This is the mean for males. This is the variance for female. The variance for female is 122,396.2857. And this is the variance for male, which is just 6,867.809524. So you can see that there is a significant difference between both values. But this is not how we interpret. We only interpret using this F critical one tail and F value. So we simply say the F value is greater than the critical one tail value, which is this. Therefore, we reject the null hypothesis, which states that the variance of both groups are equal. So how do we perform this? This is quite different from what we had earlier. And I think I've already put the illustration here. So to carry out this test, all you need to do, you click on the data tab on your Microsoft Excel, go to analysis group, click on data analysis, then select F-test to sample for variances. Then OK, then enter the variables 1 and 2 range, then choose out this range, then click OK. Then you get this result. Now let's quickly do this and see how it works. Now I have that here. So these are my observations. Okay, to carry out the F-test, all you need to do, you go to data tab. You see data tab here. Okay, so under the data tab, towards the hand here, you have analysis. If you don't have this on your own, okay, all you need to do, you click on File, okay, and you go to Options, okay, you go to Options, then you click on Headings, okay, you click on Headings, then you go to Manage, and you click on Excel Headings, okay, and you click on Go, okay, then you come here and select Analysis Toolbar. You can see mine is already checked. If you don't have this on your phone, this will not be checked. So just check this and click OK. Once that is done, you will see another data analysis whatever here. Okay, but because I already have it, I don't have to click OK. I don't have to do it, so I just close. So now you select and you click on data analysis right here. Then you go to F tests. Those sample variances. This one. Okay. Then you click OK. So now you will be prompted to enter your variable 1 range and variable 2 range. Okay. So to enter your variable 1 range, you click on this up pointing arrow button. So once you click on this guy will open. So all you need to do, I will select my finger and drag down. Select hold and drag. Okay. And you can see the cell references have been captured in here. So just click this down pointing arrow and that will appear here. So I need to select the variable 2 range as well. So I click on the up pointing arrow for this second text box. So I click this. Then I come here, select hold and drag to the last value. Then you see that the cell reference will also be captured accordingly. So you click on this down pointing arrow. You can see both text boxes have been filled up. Now, if you notice, you realize that I captured the labels alongside with it, which are female and male. Okay, so I want to tell this tool that the first row is actually the label. Okay, so in that case, I need to check this. Okay, so I check this. I'm using alpha of 0.05. So I also want to choose the attribution where I want the result to appear. So I click on this and I click on this and I select, I can select this, you can select anywhere, okay? It depends on what you want. So I selected this cell and this cell reference appeared here. Then click on this pointing arrow. So everything is done. So all I need to do is just click on OK. So once you click on OK, this is what you get. So when you look at this is the same value I have on my slide. Okay, so this is how to perform F tests on Microsoft Excel. So now I have the same value as what I have here. So I can straight away interpret by saying that since my F value is greater than this, then I reject, or we can straight away reject the null hypothesis that states that the variance of both groups are equal. Okay, so that's on F test. Now we can also perform ANOVA. ANOVA stands for analysis of variance. And when do we use this? We use ANOVA test when comparing between more than 2 groups. If you remember, all we have been doing is, the first example is 2 groups, condition A and B. That's just 2 groups. The second example is also 2 groups, but this time I have 2 different groups. Then in a situation whereby you have more than 2 groups, how do we handle that? So in that case, you can use ANOVA. If you have a simple two groups, something like, because simple three groups like this, there are some three groups that can be complicated, that can be complex. Okay, maybe later I'm going to show you one example. But if you have a basic three groups like this, then you can straight away learn a way or simple any type of ANOVA on MS Excel. And also, to perform this, we have to state our null and alternate hypothesis. The null hypothesis always states that the variance of the three groups are equal. That is, the three groups have equal variances. So while the alternate hypothesis always states that the variance of the three groups are not equal. Okay, so how do we do this? We follow the same pattern that we use for F-tests. Okay, and once that is done, you're going to have something like this. You have a summary table which has all your descriptive statistics, which shows the counts of the observation, the sum of each of the observation of the group, and the average of the group, and the variances. Okay, so then the ANOVA table is where we check for p-value to be sure to determine whether to accept or to reject our null hypothesis. But in this case, you will see that the p-value here is 0.02, which is less than 0.05. Okay, so in this case, we reject the null hypothesis that states that the difference, the value, the variance of the three groups are equal. So meaning that the differences between them is significant. That's what this actually tells us. That's what this value actually tells us. So as a result of this, we reject the null hypothesis that states that the variance of the three groups are equal. And even if you look at the variances here, the variance for young is 16.32222, while the variance for middle is 8.988888889, and the variance for old is 9.822222. So the three variances are not equal. So as a result of that, we reject the null hypothesis. Okay, so let's see how this can be done. So now these are all my observations. Okay, so I want my report to appear somewhere here. So again, like I did earlier, you click on data tab, then go to data analysis. Then this time around, we have ANOVA. So select single factor and click OK. Here we have input range. Only one text box appears. So you need to select all the guys you have here. Select, click, hold, and drag to cover every observation, including the heading. Okay, and of course, group by columns. That's a group by columns. So then label for the first row. Okay, when I want my output to appear, I select this, click on this, and I want it to appear. Maybe here is fine. So click here. Then everything seems to be set. Then just click OK. Then you have this. Okay, if you want this to be easier for you, just round it up to 2 decimal places. Okay, then you have 0.2. Okay, so this is how to investigate whether the variances of three groups are equal or not. So if you are using two groups, you want to check whether they have equal variance or not, you can use F-test. If you are trying to investigate equal variances for more than two groups, then you can use ANOVA. And if you want to carry out ANOVA on MS Excel, this is how to do it. Okay. There are other things we're discussing, especially on ANOVA in our future class. But for now, we're just investigating on equal variances when we have more than two groups. Yes, that's what I just said now. 2021. Yeah, I mentioned it now. Yeah, can you share your screen for a while? Can you share your screen very quickly?
Oh, okay. Share screen.
Yeah, please. Okay, go to file. Go to file. Yes. Go to options. There's options down there. Options. Yeah. Then go to add-ins. Click on add-ins. Yes. Add-ins. Yes. Yes. Just click on it. Hold on. No. No, you have not done it. Wait. Go back. Options. Add-ins. Click on it. Aha. Then come down to manage. Manage. You can see manage down here. Can you see this? Yes. It's already selected as Excel add-ins. Yes. So click on go. Okay, now check that, please. Check. Yes, click OK. No. No. This is the first one. Yeah. Then click OK. Yeah, that's all. Now you have it. Can you see?
Okay, thank you.
Stop sharing.
Thank you very much.
So that is that on non-parametrics test and ANOVA F-test and T-test. We're still going to do more on ANOVA and T-test later. I think we're going to have a complete class on T-test. Okay, but just to get us familiar with this analysis, at least from the point of Excel. We'll be using more of SPSS later, but just to show you that what can be done on SPSS can also be done on Excel, but it is easier and faster on SPSS. That's why many people don't really want to use Excel. But again, it's good to still get familiar with how to carry out those tests on MS Excel. Now, let's quickly discuss on non-parametric statistical tests. When data fails to fulfill the assumption of a parametric test, that is, when those assumptions, test for independence and test for normality, once your data set fails those two assumptions, then you have no choice than to use non-parametric statistical tests on such data sets. And we have a lot of them. So researcher hopes for non-parametric tests given the fact that they are less restrictive. So the test can also be used for small sample size of less than 30, and when the variables are non-metric, that is, not based on the meter as a standard of measurement. So non-parametric tests also assume that the variables are measured on the nominal or ordinal scale. We have a lot of them. We have chi-square tests, we have Fisher's exact test, we have Whitney U test, we have McLean's test, we have recursive sum rank test, we have recursive side rank test, we have Kruskal-Wallis one-way analysis of variance, and we have Spearman correlation, and a few other ones. These are just some of them. So let's quickly look at the first one, which is actually chi-square test. We want to see how to compute this chi-square test on Microsoft Excel. This can also be done on SPSS, even faster. So in this example, we have a sample of 200 people that visited a local pub. We want to perform a chi-square test of independence to see if there's an association between gender and smoking status among these people. We want to investigate. So note this now, we use t-test to investigate differences. We use chi-square to investigate whether there's an association between certain group and something. Okay, so now we want to see if there's an association between gender and smoking status. So in that case, we have the following hypothesis. Our first one hypothesis says that there's no association between gender and smoking status. While the alternate hypothesis says that there's an association between gender and smoking status. So if the first non-hypothesis is correct, then we are going to say HO will be accepted. That is, HO will be accepted if our p-value is greater than 0.05, and H1 will be rejected. But if our p-value is less than 0.05, then our null hypothesis will be rejected and our alternate hypothesis will be accepted. So that is the general scenario. That is how this actually works. Now, how do we compute this? We have 200 people. We have 200 people. How does this distribution look like? These are the people we record. These are the people we sample directly. Okay, so we have something like this. These are the observed data. We have smokers, non-smokers. So for male, we have 29 smokers. And we have 71 non-smokers. For female, we have 16 smokers and we have 84 non-smokers. Among the group of people, among the 200 people that were sampled. Okay? And when you sum this together, you should be getting 200. This is what we have. So, but this is not enough for us to compute our chi-square, to carry out our chi-square. So the first thing we need to do after having this observation is that we need to perform few summations. That is, we need to get our row sum and column total. That is row total and column total. Meaning that 29 plus 71, the total should be recorded here. 16 plus 84, the total should be recorded here. 71 plus 84, the total should be recorded here. Then 29 plus 16, the total should be recorded here. We need to get the column total and the row totals. So eventually you should have something like this. So once that is done, we need to create our expected observations. Okay, so we are going to have the same structure like what we had here. So how do we now compute this? To compute this, there is a formula, general formula that you need to follow. And the formula is row total multiplied by column total, all divided by the overall total. I'll take that again. Row total multiplied by column total, all divided by overall total. That will give you the values you have in here. So for this first guy here, for this first cell here, you need to get the row total of this place multiplied by the column total, which is 45, and divided by 200. That will give you 22.5. Same is done for this one. And here, we also get the row total, then the column total, which is 155, multiplied by the column total, 155, then divided by 200, which is the overall total. That will give you this. Same will be repeated for this. So you will get your expected values here. So once you are done with this, you should have something like this. Then you can now compute your chi-square in here. And to compute the chi-square, there's also an object of chi-squares class that you can use. And one of the methods under that particular class is test, just like what we had for the t-test. Okay, so you choose that, and you also fill in the parameters. It takes only 2 parameters, and the first parameter is for the observed value, what you had here. And the second parameter is your expected values, what we had here. Then you put all together, I press enter, and this should give you your p-value. So based on whatever value you get here, you check if it is less than 0.05 or it's more than 0.05. But in this case, because it's less than 0.05, we accept our alternate hypothesis that says that there's an association between gender and smoking status. And we reject the null hypothesis that says that there's no association between gender and smoking status. Okay, based on this. So let's see how this can actually be done. So in this case, I have this data. So these are my observations. So I need to get the sum of this, the sum of the row column. So I can straightaway say this is equal to this plus this. Press enter, and I can select this and move it here to get this guy. So here, I can also say this is equal to this plus this. Okay, press enter. Then I can do the same thing. See, just drag and drop. This will be computed for you. So I need the summation of this, which is the overall total. When you sum 155 plus this, you get 200. When you say 100 and 100, you also get 200. So whichever one you want, you can always, or simply, you can just click here and drag this one here. That sum up these guys for you. So you get, I've gotten my column total. I mean, these are my row total. Sorry, these are my row total. And these are my column totals. Okay, so I need to use this to compute this guy. So all I need to do, I can say this is equal to, I can open the bracket, row total multiplied by total divided by overall total, which is this, and press enter. So I got this. So I'm going to do the same thing here. This is equal to my total. I can put something like this. My total multiplied by my column total. This for smokers, right? My column total all divided by over total. So this will give me this. For here, I can say this is equal to my row total multiplied by my column total, then divided by my overall total, which will give me this. This one also the same. So I can say my row total multiplied by column total, all divided by my overall total. After this. So I've computed my expected values. Okay? So now the next thing now is to get my p-value. So I want a p-value to appear here. So I just say is equal to, then I type in CHI. Now you can see I have CHISQ, that's chi-square, everything is there, but I'm interested about the test. So I'm just saying GISQ.TST, then open brackets. Now I have two parameters, actual range and expected range. And you can see the actual range is what is bold now because it's expecting you to enter the values for the actual range. Okay, so the actual range will come from the observed value here. So all you need to do is click on this, click, drag, click, hold and drag, rather. Click, hold and drag. So I've done that and I release. Then the cell references for those values has been recorded. So all I need to do is just put comma, and now the expected range has been selected. So that's why the expected range is now bold. So to do that, you click, hold, and drag over all those values. Then you release. Then you have this. Then you close this, and you press enter. Then you get this value. Okay, to make it clearer, you can reduce it to 2 decimal places. Okay, and this will give you 0.03. And 0.03 is less than 0.05. And that was why we accepted the alternate hypothesis. Okay. That's how we accepted the alternate hypothesis because of the values, because of the value we got here. Okay, so this is how to compute chi-square test in MS Excel. So that is that on that for now. So what examples of statistical analysis could be? We have, if we want to compare mean between two independent groups. Okay, for example, the managers who are men have higher average salary than managers that are female. In that case, you can perform two sample T tests. If your data set or whatever you have here is, they violate the assumptions of a parametric test, then you can use Wilcoxon rank sum test. That's an example of test that comes under parametric test. We are trying to compare two quantitative measurements taken from the same individual. For example, examine students' diagnostic test results before and after a unit of study. In that case, you can use PAT test. That's the example of the first test that we carried out, the first test that we did. So, but if this your observation or your data set fails the assumption of a parametric test, that is, maybe it's not normally distributed or it's not independent, then you can use the Wilcoxon rank test. If your scenario is that we're trying to compare mean between 3 or more independent groups, okay, for example, is there a difference in crop yield if a farmer uses fertilizer A, B, or C? Then for parametric tests, you can use analysis of area, which is ANOVA. For non-parametric tests, you can use Kruskal-Wallis test. In a scenario whereby we are trying to estimate the degree of association between two variables, the degree of association between two variables, how strong is association between two variables? Then, or for example, you can say, does the number of hours a person spends on social media affect the number of hours they sleep at night? So in that situation, if you want to carry out the parametric test, you can use Pearson coefficient of correlation. For non-parametric tests, you can use Spearman's rank correlation. Okay. So the first question that will be coming down, you have to be clear about now is when to use parametric tests and when not to use. I want to use non-parametric tests. When to use parametric tests if your data set complies with the assumption of non-parametric tests or assumption of parametric tests, which are basically two. One, the observation must be independent. Two, it must be normally distributed. So once these two assumptions are met, then you can go with any of the parametric tests. But if any of one or both assumptions are violated, then two things. Check whether they were violated as a result of human error. Maybe you made some mistake while entering the data. But if that is not the case, if the data set actually fills those assumptions naturally, then in that case, just go with non-parametric tests. Okay. So these are just few examples on scenarios that warrant scenarios and kind of tests that can be used in those examples, in those scenarios. This one, we have Z-test and we have T-test. Like I said, we're still going to discuss more about T-test later, but again, this is just a very quick handy rule of thumb that can really be applied. The first question is or are the sample size greater than or equal to 30? If they are greater than or equal to 30, the next question you'll be asking yourself is how many samples of data do you have? But if they are not, the next question you'll be asking yourself is, do you know the population variance? If you know the population variance, that takes you to how many samples of data do you have. But you don't know the population variance, how many samples of data do you have still? So, yeah, how many samples of data do you have? You have one. You can say to you perform one sample Z-test. You have two. Are the two samples independent? If yes, perform two sample related Z-test. If no, perform two sample related Z-test. Here, how many samples of data do you have? One, you can perform one sample T-test. Two, are the two samples independent? If yes, perform two sample unrelated T-test. If no, perform two sample related T-test. That's just a brief guide on which test to choose and when do I choose them. Now we have other few tests. One is univariate. We have bivariate and we have multivariate. For univariate, here, it's built with only one variable. Univariate analysis deals with only one variable. Okay, and it's also known as a single variable analysis. It doesn't deal with causes or relationship, unlike regression. Its major purpose is to describe data. Okay, its major purpose is to describe data. So you take data, summarize that data, and find pattern in the data. Our method to describe patterns found in the data include, we have central tendency, which include mean, mode, and median. We have dispersion, which are range, variance, maximum, minimum, quartiles, which include the interquartile range. And we have standard deviation. So these are the methods you can use to describe pattern in a particular variable. Graph or chart for this purpose include, we have frequency distribution tables, we have bar charts, we have histogram, we have frequency polygon, we have pie charts. So these are the graph or chart that can be used to graphically present this kind of variable. Okay. We have bivariate analysis, which identifies the relationship between two variables. It's always true. So it is a form of statistical analysis used to find out if there is a relationship between two sets of values. So it usually involves the variables X and Y. For example, the association between smoking and lung cancer. Another example could be if you want to find out the relationship between calorie intake and weight. Calorie intake will be your independent variable, X, and weight will be your dependent variable, Y. With bivariate analysis, there is a Y value for each X. So let's say you had a calorie intake of 3,000 calories per day and a weight of 300 pounds. So you will write that with the X variable followed by the Y variable. So 3,000, 300 pounds. So you can have something like XY is equal to 100, 56, 23, depending on the number of subdivisions. Then common example of bivariate analysis include we have scatter plots, we have regression analysis, and we have correlation coefficients. So these are the kind of analysis that can be performed or that can be carried out on this kind of bivariate analysis. We also have multivariate analysis, which identifies the relationship between more than two variables. More than two variables. For example, we want to investigate the association between alcoholic, smoking, and lung cancer. So multivariate analysis is used to study more complex set of data than what univariate analysis method can handle. So this type of analysis is mostly performed with software such as SPSS or SAS, as working with even the smallest of data sets can be overwhelming by hand. Okay, so multivariate analysis method include additive trees, we have multidimensional scaling, we have cluster analysis, we have principal component analysis, and so on. So which method you choose depends upon the type of data you have and what your goals are. Okay, so that's what will determine the method you will be applying in your analysis. Okay, so that is, then also we have few methods of data presentation. We have tabular, we have simple table, complex table. I mean, we're trying to present your data set, your data in the tabular form. You can have a simple table, you can have a complex table, depends. Then for graphical, we have quantitative data, we have quantitative data. For quantitative data, we have histogram, frequency polygon, we have frequency curve, we have line chart, we have normal distribution curve, we have cumulative distribution curve, we have scatter diagram. For qualitative data, we have bar chart, pictogram, pie chart, map diagram, and so on. Okay, let's look at data tabulation. Tabulation is the first step before data is used for analysis. You need to first create your, first sort of data entry. Okay, so this data entry is done in a table. Meaning that you need to have some table heading and the likes. So before you enter your values. So tabulation can be in form of simple tables or frequency distribution table that the data is split into convenient groups. So a good table should include the following parts. We have the table number and title. Of course, you need to have a table title, there's a caption, and that must be cited within your text. I'm talking about your thesis now. It has to be cited inside your text. I think I've shown you how this can be done in 2 or 3 classes ago. So caption subhead, this refers to columns and rows, and body which contains all the data under each subhead. You also need to specify your source, which indicates if the data is secondary and it should be acknowledged. That means if you compute the data yourself, let's say you gather and do everything, it's okay, you don't need to add any source. Or if you want to add any source, you can say researcher's computation. But if you copied the data from somewhere, you need to put the source of that particular table under your table. Okay. So, example, you can have something like this. Will be table 1, distribution of 50 patients at the hospital in October 2022, according to their ABA blood groups. Then we have something like this. We have ABO, frequency 12, 18, 5, and 15. When you sum this up, you get 15. Then the percentage of this in here is 24. Percentage of this is 36. Percentage of this is 10. Percentage of this is 30. So when you sum this together, you get 100%. Okay? You can also have it like this. You can have it like this. So it depends. Then you can have another sample of table like this, which could be in range. Unlike the previous one that were just block book, right? So you can have it in range, something like this. So you can have table 2, distribution of 50 patients at the hospital in February 2022 according to their age. You can have age in years, frequency, and percentage. So less than 20, you have 12. Between 20 and 29 and 39, you have 18. Between 40 and 49, you have 5. 50 plus, you have 15. And these are the percentage. And sum this together, you get 15. Sum this together, you get 100. You can also have something like this. So it depends on how you want to go and the kind of data set you have collected. You can also have complex frequency distribution table. Something like this. You can have distribution of 20 non-cancer patients at the hospital and 40 controls in January 2022 according to smoking. So you can have smoking under which you have non-cancer cases and control, and you have total. So under cases, you have number, you have percentage. Under control, you have number and percentage as well. For smoker, you have 15. For under cases, for control, you have 8. And for non-smoker, you have 5. Under cases, you have 32 under control. Total 20, total 40. Sum this together, you get 100%. Sum this together, you get 100%. So for this total here, you sum this plus this, that will give you 24. Sum this plus this, that will give you 37. So sum this together, you get 60. And this sum up to 38.3%, 0.3% of the entire figure here, of the entire patient. And this sum up to 61.67% of the entire patient. When you sum this together, it gets 100. So this is an example of a complex frequency distribution. It might even be more, it can even be more complex than this. Okay? So, but these are all frequency distribution tables. Now we have graphical representation. A graph or chart portrays the visual presentation of data using symbols such as line, dot, bars, or even slices. So it depicts the trend of a certain set of measurements or shows comparison between two or more sets of data or quantities. And when it comes to graphical representation or presentation, we have quantitative data under which we have histogram, frequency polygon, scatter diagram, and line graph. For qualitative data, we have bar charts as well as pie charts. All these can be computed on MS Excel, can also be computed on SPSS. Okay, we're going to see how some of this can be done later on SPSS. Then for nominal data presentation, there's possibility for you to present your data in a tabular form. You can also use bar chart and you can use pie charts. So meaning that you can present your data in different ways depending on your requirements. If you look at this, for example, 2.1, frequency and relative frequency distributions. We have area, accounting, finance, general management, marketing, sales, order. Our total is 253. Now accounting is 73. Finance is 52, general management is 36, marketing or sales is 64, order is 28. Now, 73, which is accounting, sum up to 28.9% of the entire area. So finance, which is 52, sum up to 20.6% of the entire area. General management is 36, which sum up to 14.2% of the entire area. The marketing, which is 64, sum up to 25.3% of the entire area. While other is 28, which sum up to 11.1% of the entire area. So when you sum up this together, this will give you 100%. So this is what frequency distribution table is all about. You must have this column. Okay. Now, if you don't want to represent or if you don't want to present your data in this way, you can use pie charts. So you have 1, 2, 3, 4, 5. So we are going to have they call it legend or so. I can't remember the name precisely. That will tell us what 1, 2, 3, 4, 5, 6 actually means. Okay, so you can have something like this. So this one is actually the accounting. So this shows you that this one, which is actually 28.9, has been rounded up to 2 decimal places. That's why you're having 29 here. Okay, and for 2, which is actually finance, which is 21, so it's actually has been rounded up to 21. And 3, which is general management, which is 14, has been rounded up to 14, so 14.2. And 4, which is marketing, okay, marketing or sales, is supposed to be 25.3, has been rounded up to 25. And 5, which is order, which is supposed to be 11.1, has been rounded to 11. So this can also be represented this way. And also you can have a bar chart like this. So it is all the same information based on the same data, just different method of presentation. Okay? So if you like, you can use any of these. And sometimes you may want to use something like this. Sometimes you want to use something like something. It depends on it depends on your choice. Okay. Now we have summary statistics, which is basically mathematical presentation. So summary statistics summarize and provide information about your sample data. It tells you something about the values in your data set. This includes where the mean lies and whether your data is skewed. It falls into 3 main categories. By the way, before you go into this, once you run your analysis on SPSS, the first table you will see is always your statistic table, which is actually the summary statistics. Okay, show you the mean, show you the standard deviation, show you few basic statistics of what your data is, which allow you to inspect, to understand the pattern and what you have in your data. So if you have some kind of errors, you will have seen it there. Okay, so it falls into 3 main categories. We have measure of location, we have measure of spread, and we have graph or chart. So for measure of location, which also called central tendency, we have mean, which also called the arithmetic mean or average. We have geometric mean used for interest rate or other types of growth. We have trimmed mean, the mean with outliers excluded. That is a piece of data that is an abnormal distance from other points. Take, for example, you have a categorical variable, which changes only to value, let's say gender, for example. And you have 1 to represent male, you have 2 to represent female. And suddenly you realize that during your data entry, there are some, let's say you're supposed to enter about 200 values or 500 values, and you realize, and all those values should not go outside 1 and 2. And you realize that maybe due to human error, you went ahead and enter, let's say, enter 5, you enter 10, you enter 8, you enter 9 in some cases. So those values will amount to outliers because they will surely give some errors because they are outside the declared range. Okay, so in that case, there are some analysis that when you perform, when you carry out using this kind of wrongly enter the values, it will affect your analysis, such as regression. Okay, but there's another test to check whether your data set has outliers or not, which will be seen in the later classes. Okay, so from there you can see whether there's an outlier in what you have entered or not. Then if there is, you go straight and go and identify where the error, where the outliers are, then go straight and go and take them out. Or how do we undo outliers? We're going to discuss in our later classes as well. Then median is also the median of a data set, which is also one of the measures of location. Measure of spread, we have range, how spread out your data is. We have interquartile range where the middle 50% of your data is. Quartile are boundaries for the lowest, middle, and upper quartile of data. Skewed, does your data have mainly low or mainly high values? Kurtosis, a measure of how much data is in details. Then we have graphs or charts, where we have histogram, frequency distributed table, box plots, bar chart, bar charts, scatter plots, pie charts, and so on. So we'll look into some of this when we get to SPL, but of course, we cannot cover all. Now, determine the appropriate statistical tests. What statistic test should I use for my data? Regardless of which strategy for the statistical analysis method you pick, try to take exceptional note of every expected drawback, just as they are different formula. There is no highest quality level or wrong or right techniques to utilize. Don't say that actually this test can be used for this, but they said that this one is better, this one has more value. No. Eventually, you get the same result. So there's nothing like this one has a higher quality. This particular test has a higher quality. Both will give you the same results. So use the techniques. As long as you choose the right technique, the correct technique for your data set, then you are good to go. So it will rely upon the kind of information you have gathered, the kind of data you have collected, just as the bit of knowledge you are hoping to have as a final product. So you must know what your expected results should be. So, and based on that, you must be, of course, if you have gathered the kind of data, based on the kind of data, if you are able to identify the kind of data you need to collect, and you create or design your data collection instruments yourself, then you should be able to know the kind of, and you are able to select your analysis test correctly, then you should be able to know the kind of results you'll be expecting. So that when the result says otherwise, you'll be able to detect immediately. Okay, so, but don't think that there's a better tool or a better analysis techniques to use is apart from the one you have selected, because eventually this test you are saying that is better will still give you the same result. Okay, so that is how to determine which statistical test to apply in your research work. Okay, so that is all for today. I will share the attendance link in the chat group. Please fill it up. I've already posted it. So that is that on that. So if you have any question, please let me have them. So we have come to the end of today's section. So I've already posted the slide, and I've already posted the Excel sheet as well. So please go through and practice. Practice. You have enough time to practice now. Okay. So please practice, and if you have any issue, you can always reach out and we can always discuss. Okay, so in our next class, we'll be working with SPSS. So again, if you have not done the installation, please try to do it before our next class. Okay, so thank you, stay safe, and see you again next week. Bye.